previous two lectures I have discussed certain desirable properties for estimators. However, still we are not clear how to derive estimators for various kind of parameters. It may be one thing to say that we can estimate a population mean by a sample mean, a population variance by sample variance, or a population range by sample range, but many a times we are having more complicated situations, and moreover as we have already seen such as uniform distribution or an exponential distribution, that we may have several estimators, maybe one is based on the mean, another is based on say order statistics, etcetera. So, there must be some procedures or methodology by which we should be able to derive the estimators. So, some of the well known methods which are used are the method of moments, the method of least squares, the method of minimum chi-square, then maximum likelihood estimation, and then there are certain new procedures such as Bayes estimation, minimax estimation. The last two procedures which I have mentioned, they are based on decision theoretic concepts, and we may not be able to cover much of this in this particular course. Historically, the method of moments seems to be the oldest one, introduced by Karl Pearson. So, let me start from here. The method of moments. Let us consider that we have a random sample x 1, x 2, x n be a random sample from a population with say distribution which is identified as say p theta, theta belongs to theta. So, here in general I am considering theta to be a vector parameter, that means theta may have components say theta 1, theta 2, theta k. As we have already talked about, for example, if we consider a normal distribution, usually it is characterized by two parameters mu and sigma square. So, in that case theta is mu sigma square. Similarly, if we consider a Poisson distribution, it is characterized by a single parameter say lambda. We may have a Weibull distribution, we may have a gamma distribution. So, these are variously described by 2, 3 or 5 parameters etcetera. So, in general if we have a k dimensional parameter, we consider k moments. So, let us consider first k non central moments. That means, we calculate say mu 1 prime, which is expectation of say x 1, that is now all of these moments they are going to be functions of the parameter. So, let us call these functions as say g 1 of theta. Similarly, mu 2 prime, that is the second moment of this distribution, this will be another function of theta, let us call it g 2 and so on. Let us write say mu k prime is equal to expectation of x 1 to the power k, that is g k of theta. Now, we assume that these k equations, so each of this is a function of theta 1, theta 2, theta k. So, we assume that these equations 1 they have solutions. Assume that the system of equations 1 have solutions Now, the solutions will be in the form, that means, I am saying theta 1 is h 1 of say mu 1 prime, mu 2 prime, mu k prime, and so on. Theta k is h k of mu 1 prime, mu 2 prime, mu k prime. Let us call it 2. In method of moments, what we do, in place of this mu 1 prime, mu 2 prime, mu k prime, which are the first k non-central moments of the population, we substitute these by the corresponding sample moments. So, let us define say sample moments as define the first k non-central sample moments. That means, let me define say alpha 1 is equal to 1 by n sigma x I, alpha 2 is say 1 by n sigma x I square, I is equal to 1 to n in general. So, alpha k is equal to 1 by n sigma x I to the power k, I is equal to 1 to n. In method of moments, we estimate kth population moment by kth sample moment. That is, I am writing that mu j head, mu j prime head is equal to alpha j, for j is equal to 1 to k. So, these values we substitute here. Thus, the method of moments estimators of theta 1, theta 2, theta k are defined as theta 1 head is equal to h 1 of alpha 1, alpha 2, alpha k, and so on. Theta k head is equal to h k of alpha 1, alpha 2, alpha k. Now, the question may come that if we are having the solutions to these equations, if the solutions to these equations are obtainable in the explicit form, then only we can write down this solution for the method of moments. There may be some cases where you may have say 2 parameters or 3 parameters, but 2 or 3 equations may not lead to the solutions. In that case, we may take extra moments here. So, let me start with certain examples here. The simplest one, for example, I may consider say x 1, x 2, x n follow a Poisson lambda distribution. Now, this is a one parameter case. So, I need to take up only the first moment. Now, we know that the first moment of the Poisson distribution is lambda and the first sample moment is x bar. So, lambda head is equal to x bar. So, this is the method of moment estimator of lambda. Let us take say x 1, x 2, x n following normal mu sigma square distribution, where both mu and sigma square are parameters here, unknown parameters. Let us take here mu 1 prime. In normal distribution, the mean is mu 2 prime is equal to the second moment is mu square plus sigma square. So, if we solve this, we get mu is equal to mu 1 prime and sigma square is equal to mu 2 prime minus mu 1 prime square. So, this is the system which is equivalent to this system, that theta is are written in terms of the mu I primes. So, now we substitute alpha 1 for mu 1 prime and alpha 2 for mu 2 prime. So, the method of moments estimators for mu head, mu, let me call it MME, that is denoting the method of moments estimator of mu. It is simply x bar, that is alpha 1, and for sigma square it is equal to alpha 2 minus alpha 1 square. Let us see what is the value of this. It is 1 by n sigma x I square minus x bar square, which I can write as 1 by n sigma x I minus x bar whole square. Notice here, in the previous classes when I was discussing unbiased estimation, I derived the unbiased estimator of sigma square as s square, that was 1 by n minus 1 sigma x I minus x bar square. So, there is a clear cut case of comparison between the method of moments estimator and an unbiased estimator in this particular problem. Let us take say x 1, x 2, x k following a binomial distribution with parameters n and p. Quite typical situations in binomial distribution deal with the situations where n is known. So, if we have n is known, then parameter is p here, and if I consider the first moment here, first moment of the binomial distribution is n p. So, this is to be estimated by alpha 1, that means x bar is an estimate of n p. So, if we want to write down the solution, p is equal to mu 1 prime by n. So, we get here p head is equal to x bar by n. So, this is method of moments estimator of p. Since here only one parameter was there, we considered only one equation. Now, let us take the more general case where n and p both are unknown. When both are unknown, then we will have to take up the first two moments. So, mu 1 prime is equal to n p and mu 2 prime is equal to n square p square plus n p into 1 minus p. In the binomial distribution, the second moment is equal to this value here. Now, we can solve this equation. Actually, if we take up say mu 2 prime minus mu 1 prime square, I get n p into 1 minus p. So, if I divide this equation by this, I get 1 minus p is equal to mu 2 prime minus mu 1 prime square by mu 1 prime. So, the solution for p has come, and if I substitute that value of p here, I get the value of n. So, I get p is equal to 1 minus mu 2 prime minus mu 1 prime square divided by mu 1 prime, and n is equal to mu 1 prime by p. So, now by substituting alpha 1 and alpha 2 for mu 1 prime and mu 2 prime, I get the method of moments estimator for n and p. So, let us look at this value here. We get p head MME as 1 minus alpha 2 minus alpha 1 square by alpha 1. Here alpha 1 is x bar and alpha 1 square is 1 by n sigma x I square. So, if you substitute those values, this turns out to be x bar minus 1 by n, in this case it is 1 by k sigma x I minus x bar square I is equal to 1 to k divided by x bar, and n is estimated by x bar square divided by x bar minus 1 by k sigma x I minus x bar square I is equal to 1 to k. Notice here, when n was known, then the estimate for p was simply x bar by n, whereas now you can see it has changed quite drastically here. In the context of these exercises, let us also see some other properties which we had earlier. For example, unbiasedness. Now, you see in the Poisson distribution case, expectation of x bar is equal to lambda. So, the method of moments estimator is actually unbiased. It will also be consistent if we apply the weak law of large numbers, as we have already seen that if the first moment exists, the sample mean is always a consistent estimator for the population mean. So, in this case MME is unbiased and consistent for lambda. Let us take up the second one, normal distribution example. Here if we are looking at x bar, then x bar is unbiased for mu and also it is consistent. However, if we look at the estimator for sigma square, you can notice here that it is not unbiased. However, it will remain consistent because it is actually n minus 1 by n s square. So, since s square was consistent and n minus 1 by n converges to 1, this also converges to 1. Therefore, here you are having that mu head MME is unbiased and consistent. However, sigma head square is biased but consistent. So, this brings us to important property that the unbiased the method of moments estimators need not always be unbiased. Now, in these two exercises they are consistent. So, again the question arises whether they will be consistent always. Let us take up the next case. Here x bar by n, this is unbiased as well as consistent. So, p head is unbiased and consistent. Let us take the second case when both the parameters were unknown. Here if you see, since x bar was unbiased for p, so this cannot be unbiased because this is quite different. If we take up the limits here, so we are having x bar converges to n p in probability, we are having 1 by n sigma x I square, that is alpha 2, this converges to the second moment, that is n square p square plus n p into 1 minus p. So, both of these are convergent in probability. Now, let us look at this quantity. In the denominator you are having x bar minus 1 by k, this quantity. So, if you look at the limit here, this is going to n p and this is going to the variance term, that is n p into 1 minus p here. So, this does not converge actually, because for convergence in probability we have established one property, that is the invariance property, but the invariance property is only for the continuous functions. Here this is not a continuous function because the denominator may become 0. However, n head does not converge to n in probability. We may take one illustration here. You may take say k equal to 2. Let me take observation, say x 1 is equal to 2, x 2 is equal to say 6. So, x bar is equal to 4, and if I calculate 1 by k sigma x I minus x bar square, that is also equal to 4. So, this denominator actually becomes 0 and the probability of this is positive because I am taking it to be actual observations here. Therefore, we conclude here that the method of moments estimator need not be consistent also. So, this is a method, sometimes the properties of unbiasedness and consistency hold, sometimes they do not hold. So, let me give it as comments here. The method of moments estimators need not be unbiased. If the functions say g i's are continuous and 1 to 1, in that case inverse functions will exist and they will also be continuous. H i's are continuous, then MME's will be consistent. That means, they are not always consistent, but under certain conditions they will be consistent. Let us take up another case. Let us take say x 1, x 2, x n, a random sample from a uniform distribution say on the interval a to b. Again you may have different conditions, for example, it may be one parameter situation, that means a may be known or b may be known or both may be unknown. So, I will consider the case when both a and b are unknown. So, that means, we have two parameters. So, we write down the first two moments, the mean is a plus b by 2 and the second moment is a square plus b square plus a b by 3. So, we need to solve this. If we solve this, we get a is equal to mu 1 prime minus square root 3 mu 2 prime minus mu 1 prime square, and b as mu 1 prime plus square root 3 times mu 2 prime minus mu 1 prime square. So, these are basically two equations in two unknowns and they are nonlinear equations. However, one can solve it by making use of certain elementary relations such as a minus b is equal to square root of a plus b whole square minus 4 a b. So, I am assuming since the interval is from a to b. So, I am taking a to be less than b. So, I am taking minus value here and plus value here. So, if we substitute the alpha 1 and alpha 2 here, then the method of moments estimators turn out to be x bar minus square root 3 by n sigma x I minus x bar square and b head MME as x bar plus square root 3 by n sigma x I minus x bar square. In this particular case, we may see that these estimators may be consistent. Now, the reason for that is that alpha 1 is consistent for mu 1 prime and alpha 2 is consistent for this, and this is continuous function here, and that is the inverse functions that we have considered, they are continuous. Therefore, this will be consistent. However, they are not unbiased here. I mentioned that if I am having a k dimensional parameter, then we may usually consider k equations. So, why usually? Because sometimes the k equations may not give us the desirable result. Let us take a very simple example. Sometimes for a k dimensional parameter, we may have to consider more than k equations. So, let us take an example for this situation. Say x 1, x 2, x n follow a uniform distribution on the interval say minus theta to theta, where theta is a positive number. Now, in this case let us see the first moment mu 1 prime is actually 0. So, this does not give any information about theta and therefore, how to estimate. So, a natural thing is to consider the second moment here. The second moment here turns out to be, if we substitute in the previous formula of this, you will get theta square by 3, because a is minus theta and b is plus theta. So, if I substitute it here, I will get theta square plus theta square minus theta square by 3. So, that is theta square by 3. So, a solution to this is equal to square root of 3 mu 2 prime. So, I may take the method of moments estimator as square root 3 alpha 2, that is square root 3 by n sigma x I square. So, here since the first moment did not give us any solution for theta, I am using second moment. I end up this section with two more examples, one for a 2 parameter gamma distribution and one for a 2 parameter beta distribution. Let us take say x 1, x 2, x n following a gamma distribution with parameters say p and lambda. So, here lambda is corresponding to the rate of the corresponding Poisson process. That means, I am taking the density function is equal to lambda to the power p by gamma p e to the power minus lambda x, x to the power p minus 1, x is greater than 0. Now, in this distribution, the first moment is p by lambda and the second moment is equal to p into p plus 1 by lambda square. So, quite easily we can solve this. The solution is in the form p is equal to mu 1 prime square by mu 2 prime minus mu 1 prime square and lambda is equal to mu 1 prime by mu 2 prime minus mu 1 prime square. So, the method of moments estimators are easily obtained as x bar square divided by 1 by n sigma x I minus x bar square and lambda head MME is equal to x bar divided by 1 by n sigma x I minus x bar square. One can easily check that these are consistent, but not unbiased. So, generally the method of moments estimators will be consistent, but usually they will not be unbiased. In fact, the typical situations where they will be unbiased is only when you are having the first moment only. So, in that case the sample mean is unbiased for the population mean and therefore, unbiasedness will be satisfied. Similarly, let us take up say beta distribution say with parameters alpha and beta. That means, I am considering the density function as equal to 1 by beta alpha beta x to the power alpha minus 1, 1 minus x to the power beta minus 1, where x is between 0 and 1 and alpha and beta both are unknown positive parameters. The first two moments of a beta distribution are alpha by alpha plus beta and alpha into alpha plus 1 divided by alpha plus beta into alpha plus beta plus 1. So, we can solve these equations by firstly dividing and then subtracting by 1 etcetera. So, the form of the solution is that alpha is equal to mu 1 prime into mu 1 prime minus mu 2 prime divided by mu 2 prime minus mu 1 prime square, and beta is equal to 1 minus mu 1 prime mu 1 prime minus mu 2 prime divided by mu 2 prime minus mu 1 prime square. So, if we substitute mu 1 prime as alpha 1 and mu 2 prime as alpha 2, we get the method of moments estimators as x bar into, well, this is x bar minus 1 by n sigma x I square divided by 1 by n sigma x I minus x bar square, and similarly beta hat MME is equal to 1 minus x bar into the same term here, that is x bar minus 1 by n sigma x I square divided by 1 by n sigma x I minus x bar square. In this case also, if we look at this thing, these estimators are consistent, but not unbiased. So, this alpha head and beta head MMEs, they are consistent, but by consistency is obvious because these things have turned out to be continuous functions. In fact, the denominator is always positive because mu 2 prime minus mu 1 prime square is actually the population variance, and if you look at these functions. So, from here, because of the basic weak law of large numbers, x bar or alpha 1 converges to mu 1 prime in probability and alpha 2 prime converges to mu 2 prime in probability. So, if we substitute these things here, these things also remain consistent. However, they are not unbiased. In fact, later on when we discuss the theory of finding out unbiased estimators, we will see what will be actually the corresponding unbiased estimators. So, today's class I end up at this point.